Good afternoon, everybody. Welcome to the next edition of Critical Canadian Building Science with our helpful sponsor for this edition, Enbridge. We have a special guest with us today, Mr. Trevor Trainor. We're going to let you folks get settled in here, give folks a few minutes to file in digitally online. As usual, it's really nice to see lots of familiar names on there. And this is a topic that keeps coming up on the requests. And it has been, I think, Trevor, ice damming this year, good year, bad year, never seen a year like with it. What do you think?
Yeah, the worst I've seen since I moved from Northern Ontario. Yeah.
Interesting. Isn't that something? Yeah, we've had an exceptional year. And so over the last couple of years, homes might have been okay, but the conditions of this last year sort of pushed over many homes over the edge. So, all right. Well, it looks like we've got a number of folks in there. So welcome. Welcome to the session. What's up with roof ice dams in 2025? Bit of a hot topic, no pun intended. Real quick, we're going to do some introductions. We'll do some housekeeping. We'll do some polls. I'll do a little bit of an introduction to the topic and a little bit of what building knowledge often sees in the field. That'll only take about 5 minutes or so, and a little reminder on the fundamental building science issue with air in the attic and ice dams. And then Trevor is going to take over, and Trevor's going to walk us through the ice dams, and then hopefully we'll have a little time for Q&A. I do want to, Trevor, I want you to have enough time to move through. And as usual, if there are Q&As we can't get to, we'll try to answer them afterwards. Brandon, we have Brandon Leiter from Enbridge with us today. Brandon, it's good to have you on.
Yeah, thanks for having me, Andy. Enbridge is always proud to sponsor the Critical Canadian Building Science webinar series, and we appreciate you guys hosting these. My name is Brandon Leiter, and my role with Enbridge is to develop and manage relationships with HVAC industry professionals in Ontario and make sure that we're listening to their feedback and providing the best possible connection experience. My focus is on new construction accounts. However, Enbridge wants to ensure that we're meeting the needs of all of our HVAC partners. So this does include retrofit contractors as well. We'd like to start today's session with acknowledging the land that which we gather on is the traditional and historical lands of the original people of Turtle Island, who have been caretakers of these lands since time immemorial. Today, this gathering place is home to many First Nation, Métis, and Inuit peoples. Our acknowledgement of this reminds us that the great standard of living is directly related to the resources of and relationship to Indigenous people, and we have a responsibility to honor that. Next. I'm just taking a quick moment here to acknowledge safety. On the topic of today, we just want to remind people, don't be going onto a roof if it's full of snow or it's icy. Make sure that you can clearly see your footing and that there's it's daytime, there's good lighting. It's always best to call a professional to help rather than trying to be a hero and do it all yourself. There's people out there that are trained and they can do these jobs very efficiently. If you must go on a roof, though, make sure that you have someone there to support your ladder and also to kind of stand by just in case, any kind of injury occurs.
Hey, Trevor, is that you in that picture?
No, that's not. Could have been, I suppose.
Yeah, that's right.
Been on a few snowy roofs this year.
So I'll just briefly mention some of our energy conservation programs for residential new construction. And these are incentivizing builders to build beyond code. Next. Energy Star for new homes. So the goal of this program is really about boosting the market penetration of the Energy Star or equivalent homes in areas that have historically had low adoption. You can contact your regional Enbridge builder rep and confirm which municipalities qualify for this offer. And if you aren't sure which rep is for your region, you can contact me and I can forward that off to you. These homes must be built in an eligible municipality that is an Enbridge gas service area. And builders can claim incentives up to $1,650 per home for up to 50 homes. One point to note is that this program is scheduled to wind down at the end of the year. So we do have reserved funding, but it will not be continued into 2026. So if this is something you've been kind of thinking about, on the fence about, now's the time to take advantage of it. And another one of our programs is a net zero energy ready. So this program is for builders who have not previously labeled net zero or net zero energy ready. And Enbridge provides expert knowledge through workshops and trainings, which do include trainings for your trade and sales teams as well. And it's really designed to guide builders through that first step of the process and make building your first net zero home that much easier. Again, the discovery home that you're building has to be located in Enbridge gas service area, and the project must be in the pre-design stage when you apply. For the builders, you have to be a member of the CHBA and a member of your local Ontario HBA as well to be eligible.
Thanks,
you,
Brandon, very much. And thanks for your help. All right, we'll get started into today. So folks, you know the rules of engagement for our webinars as usual. If you have questions pertaining to the topic, please put them in the Q&A. Otherwise, the chat is simply reserved for if something's wrong with your internet or you're not hearing things. Stacy, our webinar expert, is over there, Stacy Cooper, so she can help you and answer questions. Also note in the chat that she'll often be placing links where you can access some information. Again, please be respectful in the chat. I'm simply going to say, be good Canadians, and that's I think that says it right there. The survey is going to be sent out immediately after the presentation. Folks, that survey is incredibly valuable to us and to our speakers and to our folks. So please take a few minutes and fill it out. Please also note that the chat is not there for, I know a number of you, you work with good products and you create great homes, but it's really not intended to for solicitation or advertising. So thanks for your understanding on that. And then just the last note is that closed captioning has been enabled. So very quickly, we always like to find out where you're from and what your position is. So Stacy, let's roll the first poll. So folks, get your Zoom fingers ready and just take a minute, give us a little information where you're calling in today from. Trevor, this is always an interesting one, right? Looks like we're going to have a number of climate zones today. We got some British Columbia. We've got groups in Alberta, Saskatchewan, right? Some climate zone 7As in here. Trevor, you've done a lot of your work up in, is it climate zone 8, subarctic?
Yeah, it would be 8++ in some cases, up to 11,000 heating degree day territory.
Interesting. Very good. So lots of folks, just about every province represented here. Let's move up to see what your occupation is, if you folks don't mind. And again, if there's a category that isn't mentioned, please feel free to just put it over in the chat. And again, it provides us a little bit of context as we have these webinars. Got a number of architects, Lots of builders, renovators, developers, some consultants, got some building officials as well. Excellent to have those folks on today with us. The mechanical designers, contractors, and others. Excellent. Good. All right. We'll keep moving along. Thanks for that, folks. So Trevor Trainor, many of you folks know Trevor's not a stranger to these webinars. Trevor's also not a stranger to many of you out there. Trevor, good to have you.
Thanks for inviting me. Yeah, fun topic.
Trevor's got a few other topics too that he's helped us with. And again, those webinars are available on our website and on YouTube as well too. And I expect we'll have Trevor back in the future too, because I think we have a few more sessions on hygrothermal modeling, Trevor. I think this year we're going to be looking at some other scenarios. So
excellent.
Yeah. Then myself, of course, Building Knowledge Canada, and again, just here to sort of host and help facilitate a little bit and to sort of set the table for Trevor. So we're going to jump right into sort of the first slides, context setting. It has been quite a winter. We not only have seen lots of ice on roofs, we have seen exceptional snow loads. Loads of snow and depths of snow on roofs that typically we might not see unless you're in mountain areas, right? 2.5 to 3 feet of sitting snow on some of these roof decks. We always do like to remember too that a lot of things that have to do with ice damming may have to do with simple maintenance. So again, from the warranty providers, just a reminder that we do need to build right, we need to build well, but there also is a component of this where we do have to, as homeowners, maintain our roofs. So again, Tarian has some really good information on that about common maintenance, and I'll just give you one is let's try to clear the roof of snow when you start to get 2 to 3 feet on top of the roof. All right, let's take a look at ice dams and how they happen. This is a little graphic from our construction instruction team out in Denver, Colorado. I mean, you'll see here that what we're showing is up in this area, you'll often have a area where there is a lack of insulation or also air leakage, a little bit of both. And what happens is that warm area starts to change the temperature of the roof sheathing, causes the snow to melt and return to ice. And we start to get ice dams, and the ice works its way back up under the shingles. We get ponding, we get lakes. So again, some key things to keep in mind. I do want to bring just a real quick note to everyone's attention that, you know, the cause of ice dams, and again, this has been CMHC's take on this for years now, 50 plus years, is a lot of the cause of ice dams is air leakage, and Trevor's going to speak to that a bit. A lot of it is lack of insulation and some thermal bridging. And then, of course, we also have, in some cases, maybe too much snow on a low slope, and the snow can create a microclimate. But we'll leave that to Trevor to talk about with us. A couple things we do want to remember is that our attics and our ceilings and our roofs, the last 20 years, a lot has changed. More insulation has come in, and by virtue of that, our attics are colder. We also tend to forget that the soffit vent or the vent at the bottom of the roof needs to be connected to an area for the air to go out at the top. And then, of course, the question is, do we have enough? And then, of course, we also have lower pitch roofs. And I think Trevor's going to talk a little bit about that today, too. So all these things that have changed in the way we design, the way we insulate, and what we do to our roofs have changed really substantially over the last 20 years. The other thing, too, is just a building science reminder, folks, back to basics, right? It was Canadians and some of the Scandinavians back in the 1960s that sort of found out or discovered that as we increase insulation and we start to limit the amount of energy that's available inside our assemblies, we have to make it airtight, because if we don't, we get the stuff we see on the right. Attic frost. We start to see decay inside of enclosures, exceptional or exacerbated rotting of materials, because as we add insulation and limit the flow of energy, we also have to stop the moisture flow. Again, you've all seen this slide, right? And I wanted to just give folks a little example of, as Trevor gets into things and starts talking about air leakage, I want to remind us of just how much moisture we're talking about from an air leak. And it's a big deal. Back in the day, right? Here's Harold Orr, the builder of the Saskatchewan home, part of the Saskatchewan and also the Canadian Research Council, built, arguably probably one of the first passive homes in the world, and then built a series of homes. And that was the way they sort of looked at air leakage. It was really unknown. Up to the left, you sort of see some of the first forms of the blower door. And again, it was Harold and team that invented the blower door. Bought a little motor from down at Princess Auto, put it in a piece of plywood and developed that technology. But here's the point we want to make today is that the primary reason that air leakage was a big deal to these folks was because they wanted to understand how much moisture got into the assembly. And keep in mind, when we do a blower door test, right, we're all used to talking about ACH at 50 and the wonderful numbers we get of 1.5 and 0.6 or a 3 air change. But really, the reason fundamentally that we do a blower door test is really to find out what's happening at an ACH of 5 or 10. Because at 5 or 10 air change, that is typically the pressure differential that the home is going to experience. That's the pressure differential that's going to be between the inside of the home and the unconditioned space in the attic. And here's the interesting thing. Keep in mind that it is moisture inside the envelope in the conditioning space. This is why we actually have air barriers in our building code. Now, if you want to do a little math, we were talking about there's actually ways to calculate this from things called books, not from Google. And that calculation looks a little like this. So if you do want to calculate based on your blower door test, just how much water is going to get into your attic and walls, there's your calculation. So let's run this real quick. Let's say you've got a 2,300 square foot home. The slope of the line, the blower door test is we know what that is. We'll take a look at it in just a minute. Let's assume the house is at 20% relative humidity, so really dry. And let's assume 5 Pascal, not 10, but 5 is average pressure. When you do this on the home to the left, which has a fairly average blower door test, you'll start to see where the leakage is at 5 Pascal pressure difference, and it's in around sort of that 100 to 200 CFM range. So when you run the calculations and you do the math, that comes into about 108,000 cubic feet of air per day is actually going to be leaking into the assembly. Now, if we know the moisture content of that 20% RH air at 22 degrees C, we can tell you how much liquid water is potential in there. And that's what we use the psychrometric chart for, right? We take that 21 degree C, we run it up to 20%, we run it to the right of the psychrometric chart, and voila, we see that there are 21 grains per pound of dry air being carried in the air leakage. Now, when you do that math, here's what that looks like. Oops, I don't even know if I have those numbers. I might have to come back and get that. What it comes out to is it comes out to about 30 liters of water per day is actually going to get into the attic and into the enclosure simply from a small hole with a fairly airtight home. The other thing too that we just want to remind folks, this is the type of thing that we often see in the field. And what this leads to is some of the things that Trevor's going to talk about today. And that is air leakage where there is no caulking or sealing of the top plates. Now, we've been made aware that there are some in the industry that feel you don't need to caulk the top plates. Well, I can show you what a blower door test looks like when there is no caulking of top plates. Yes, there might be a continuous layer of polyethylene, and your blower door test, arguably, when you do the depressurization, might look good. However, what happens is if there is no caulking and clamping, the air still can get out from the air cavity and leak into the attic. And what you start to see is you start to see issues with ice damming. The other thing too that you see, and Trevor, you've probably seen this, is the same thing that often causes ice damming also causes truss uplift. Because that moist air gets into the attic, it causes wetting of the trusses. The top cords, which are wet, are also more cold, which means the moisture content goes up, which means the top cord is going to expand, the bottom cord wants to stay the same, and it starts to pull up on that member. So just a reminder that there's a lot at stake here. There's fundamental building science behind it, and I'm actually going to pass this over to Trevor now. So Trevor, I'm going to stop sharing. And take it away.
Sounds good. Let me get my screen set up here. About that. There we go. That look okay, Andy?
Oh, we're not seeing anything yet.
Not yet.
Nope.
Okay, let me go back. Oh yeah, there's always that second step to sharing.
There we go.
And full screen. How's
Beautiful.
that? Okay,
That's
great.
awesome. That looks great, Trevor. Yeah.
Great. Great. Well, thanks for introducing the topic, Andy, and for getting me involved in this, because this is just as a building science geek and as a someone who studies northern housing, this is just really intriguing and fun to think about and talk about and get into. So I did have a little section breaking down how ice damming forms, but I think Andy covered that really well in the previous explanation. So I'm just going to kind of get down to this last little slide after everything happens that we talked about. One of the cool things about my job is that I often get to get into issues after they've occurred and figure out why they've happened. And so that's where a lot of the experience and information I'm bringing today comes from, is opening up roofs, walls, etc., and finding out where that moisture problem came from. So it's just an example of how ice damming can directly cause moisture intrusion. If we have, for example, insufficient ventilation into our attic, such that we have warming temperatures in the attic, which create warm temperatures at the sheathing and cause melting of that snow layer on top, ice formation, water damming, and back up under the shingles. So this is sort of the classic ice damming case where we get ponding or on top of the roof, water backs up into the shingles and ends up inside the building. Not always, in fact, probably not even the most common reason I see moisture in roofs in the winter, but certainly is something that is worth looking at and talking about. So as we get into, or before we get into some of the hardcore science of ice damming and what the different factors that affect it are, did want to also talk about the difference between ice damming and air leakage condensation. So from a forensic investigator's perspective, I often need to try and figure out if the water intrusion that's happening in the house is coming from an ice dam on the roof, or it's coming from air leakage condensation. And so there's a few different things we need to think about. And I'm not going to talk as much about air leakage condensation, but I did want to bring it up early. And so as Andy mentioned, as warm, moist air from inside the building, let me turn on my laser pointer. There we go. Warm, moist air from inside the building is able to leak into the attic. It starts to raise the temperature and the relative humidity in the attic. If we have enough ventilation to take that moisture away, we may end up with maybe a dew point in the attic of, say, -8 degrees when it's -10 outside. And we're probably going to see a tiny bit of frost formation on the underside of the roof, but nothing significant. And that's pretty normal, and that happens pretty much all the time. Our attics are designed to be able to handle a certain amount of moisture loading during the winter, dry out during the summer. So if we have good ventilation and good air tightness, the balance in this system remains safe and we're okay. Where we start to get into issues from an air leakage standpoint is if we have too much air leakage and not enough, or not enough ventilation. And as that occurs, we end up with warmer temperatures, higher dew point temperatures inside our attic, and just more frost buildup. So for more hours of the day or of the winter, the sheathing temperature is below the dew point temperature of the air in the attic, and we start to get that frost buildup like that photo that Andy showed, where you can get significant amount of frost buildup over a cold spell, and then the first warm spell we get, all of that frost melts and ends up coming sometimes into the building through various locations. And so part of the key of trying to understand the cause of an existing problem is understanding those two mechanisms and how to distinguish between them. And I'll talk a little bit more about that as we go forward. A couple things to know about air leakage condensation and what is commonly called attic rain, which is that time when all that frost melts, is that the frost buildup can occur with or without snow or ice on the roof. So it's not necessarily an issue of snow on the roof that causes it. It's more of the air leakage condensation and the temperature outside. Certainly, if there's snow on the roof that starts to block ventilation, especially the high vents in a roof, that will affect how much frost forms because there's not as much ventilation to take that away. So that can be a factor. Primarily, though, it's just long stretches of cold weather. If you have like a cold couple of days and then a warm day, cold couple of days, a warm day, this tends to work itself out. But when we have weeks of really cold weather, maybe months at times, followed by a warm spell, that's when there's enough buildup of frost and enough melt that we can start to see it inside of our buildings, marks on the drywall, in the ceiling, coming down walls, that kind of thing. So that's always sort of when we see those is when the weather warms up, we get that warm spell. So the thing to know about air leakage is it can contribute to ice damming, but it can also be an issue unto itself. But what we will be talking about more today than attic rain and frost formation like this is how that air leakage can lead to ice damming and those issues on the exterior of the building. So real quick, a couple of Band-Aid solutions, we'll call them, to ice damming. Things that we can do quickly that will help, obviously, is removing snow. Right? And we talked about that earlier. There are actually tools designed for this. I know growing up in Sault Ste. Marie, it was my job once I hit about 14 to rake the roof every couple weeks. And it was a lot harder than this because we had a 2-story house. So it was pretty tough to get the right angle. And I did not climb up on the roof, but we were often pulling snow and chunks of ice down and trying not to have that land on ourselves. Obviously, the other one is just to heat the roof. If we heat the eave, that ice won't form. It'll melt away. Again, a real Band-Aid solution, but maybe an option if nothing else is possible or available to us. But there's definitely better ways to do this. And we can do it from a design standpoint. There we go, sorry. So let's talk about some design solutions, what we'll call not Band-Aids. So this happens to be a picture of my garage, which is not really fair because it's not fully heated. It's partially heated. But the way I built it, I feel that it would still perform really well, fully heated. We can talk a bit more about that in our design section at the end. But this was a couple weeks ago here in Stratford. We had, between 2 and 3 feet of snow on a lot of our roofs. This happens to be a steel roof with no snow catchers, so you can actually see that some has already fallen down and piled up over the winter, but a lot of it still piled up. Walking around in Stratford, which is a town that has a lot of early century homes, a lot of which haven't been updated. I could see huge amounts of ice formation. I could stand here and just go through photo after photo of huge icicles, some of which are concentrated, some of which were diffuse across the entire eave. And now I'm going around and taking pictures of the eaves trough that's been ripped off. In some cases, taking the fascia with it and soffit with it in some cases. And other photos, I could also have a small collection of ice that has fallen off all at once and crushed air conditioners along the side of the houses. So even if the water somehow manages to not go in and penetrate into the house, there's a lot of other issues that can occur when we allow this ice formation at our eaves. So in order to demonstrate some of the things we can do from a design perspective and from a construction perspective to reduce the risk of ice damming, I threw together a bit of a model. And so this is a hydrothermal model, but we're mostly using it from the heat perspective. Also just important to note, I think this is really important, is that all models are wrong and some are useful. And so
Nice.
my goal today, and that's a George Box quote, and it's more from the financial side of things. And we definitely know all models are wrong when it comes to financial models.
Yes, yes.
But even hydrothermal models, it's never going to give you the exact answer, but it can be really useful. And what I'm going to, my goal today was to provide some useful information using modeling.
Nice.
So to understand what factors affect ice damming and what sort of the order of magnitude of that effect is. So a couple things to lay out up front is some of the constants in my models, where I use the weather of Ottawa. So a little colder than Toronto. I wanted to really kind of show that colder year that we've had. Interior temperature of 20 degrees, direct applied shingles. So in most of my models, there's some exceptions I'll talk to. What I'm going to display as an output is the exterior roof temperature in January and February using this Ottawa weather file. Another constant, which I realized the model is pretty sensitive to, is the thermal conductivity of the snow that's on the roof. And I have a little more information on that before we get going. The variables I chose to look at were the thickness of snow. So we'll look at 1, 2, and 3 feet of standing snow. The attic ventilation. So we're going to look at attic ventilation at 5 air changes per hour, and half of that, 2.5. And I'll explain where those come from, because the model's pretty sensitive to that also. Air leakage from the house into the attic. And so what I'm using there are values that represent, in the best they can in a model, a house that is tested at about 1.5 ACH50, 3 ACH50, and 5 ACH50. And then finally, attic insulation. For the vented one, I'm going to look at R30, 50, and 70 of attic insulation. And then we'll talk a bit more about unvented roofs a little bit too, and some of the differences. So the results I'm going to show you, first of all, I'm going to display where that snow conductivity comes from. So this actually I found only in Canada, I guess. You can find a literature review of people that have been studying the thermal conductivity of snow since 1889 was the earliest study. Through the
Journal of Glaciology. Isn't that cool?
The Thermal Journal of Glaciology. And so, yeah, this is the culmination of all of these various studies over the years. And I got real creative and picked the very middle value for that, which, if you're curious to know, is about 1.2 or 0.125 watts per meter squared Kelvin.
Okay.
So that's where that came from. And the model is quite sensitive to that. So if the snow is really fluffy, it might be a bit more thermally or less thermally conductive. And if the snow gets packed down, it'll be less. But I'm using this 1.125 value, which is the average of averages, I think. And then the other part that really was difficult to understand is the amount of ventilation we can expect in an attic. So this is a study from BCIT. And what it looks at is predicted attic ventilation from another model. Okay, different type of model, a CFD model. And in winter and in summer, I use the winter values. And if you look here, what we're showing, the blue line is ventilation only due to stack effect.
Okay.
Whereas
which is interesting, right?
Red and black, red and black have 2 different wind factors.
Okay.
For my model, I just use ventilation due to stack effect, because that's the only one we can really count on to be a constant in to ventilate our attic. I've talked about
and that's even similar to air leakage or infiltration on buildings or houses, as it is that, like we just said, that 5 air change range, 5 to 10, somewhere in there. So
yeah, you'll get peaks much higher than that, but when it averages all out, it'll be much closer to 5.
Yeah.
We can't really count on wind in most locations, especially in cities. So that's where those numbers come from. Slightly boring, but if I don't talk about that, the models look a little questionable, I think. So what are we looking at here? So this is, the green line here, is the roofing surface temperature with no snow on the roof over the course of January and February in Ottawa for the weather model I chose, or weather year I chose. Also, the exterior temperature matches this almost perfectly. So I won't plot the exterior temperature, but it's almost exactly this as we go forward. So in this 2-month stretch with no snow, I put a blue line at 0, above which freezing or thawing will occur, excuse me. And there's just a couple tiny little hours of those 2 months where we were above 0, where melting could occur. Now we're going to look at that same model. I guess just to mention also, at this point when I'm comparing snow depths, I'm looking at a fully vented attic, I'm calling it, which is 5 ACH, R50 insulation on the floor of the attic, and air leakage into the attic equivalent to 3 ACH 50.
Okay.
So that's what no snow looks like. Let's start adding snow into the model. When we add 1 foot of snow, we can see what happens to the temperatures. Everything jumps up in the range of 2 to 5 degrees, depending on how slowly it's occurring. But we start to get longer sections and more sections where we're above freezing. Sorry, yeah, above freezing.
Okay.
Where we would expect snow melt to occur, and we're risking ice damming.
Right. So as the temperature, and this would be, yeah, okay, gotcha.
Right. Roof surface temperature under the snow.
Yeah.
So we got certainly a bit of melting here, and then only tiny little bits other than that throughout that 2-month period. What happens when we add another foot of snow? We go to 2 feet of snow, it jumps up about another degree in temperature, but nothing too dramatic. And let's just jump right ahead to 3 feet of snow. So what I learned from this is the biggest thing we're going to see is that that first foot of snow makes a much bigger difference in this surface temperature than the next 2 feet of snow.
Okay.
In a properly vented attic, with a properly vented attic, or on a roof below a properly vented attic. Okay. And so now I started to think about how do I summarize this data to make it a little more digestible. So to do that, I got to invent a metric, which I call snow melt degree hours.
And we are the first ones to hear about this. Isn't that interesting?
As far as I know, I've invented this. Maybe somebody has beat me to it, but I came about it independently.
Interesting.
So,
hey,
snow melt degree hours are the sum of the hourly temperatures when the roof surface is above 0 degrees Celsius.
Okay.
And just for reference, how many hours are there in January, February? There's 1,418 hours. But remember, we're not just counting hours, we're counting hours times how many degrees above freezing it is for each of those. Right? Okay. So when there's no snow on the roof, we have very few, I don't even know what that number is, snow melt degree hours. Doesn't matter because there's no snow on it anyways. Once we get a foot though, we're now over 500. 2 feet, we're probably at around 700 to 800, and up to about 1,000 snow melt degree hours with 3 feet of snow on the roof. Now, try and make some sense of this. Having done all the rest of the modeling, I feel that, and this is just my opinion at this point, because this is a made up thing that hasn't really been studied, but I think anything below 1,000 is pretty safe for this 2-month period. I think I'd call this the low risk zone, 0 to 1,000.
Okay.
And you'll see why as we go forward. So if we have a properly vented roof that's all areas of it are getting properly vented, we have decent air tightness, and we start to get snow on our roof, we'll get some ice damming, but probably not enough for it to become a problem, is what I'm arguing here. And let's talk about sort of the other side of it. What I also wanted to check with now what I'm calling a poorly vented roof. So a roof that has about half of what a properly vented roof is. And there's lots of reasons that could happen. Yeah. Complex roof lines, that could be due to snow covering some of the upper vents. That could be due to low roof slopes and having less stack effect
So something that would be, I know in other chats we've had, Trevor, is we do see a lot of, 412, 312,
Yeah,
212 vented roofs, and you have
right,
basically no height difference between the in
right.
and the out, right? Like
That's right.
the other one,
For stack effect to work, it needs a height difference. And the less
right?
that height difference is, the less ventilation we're going to get.
And then of course the other place too that we often see this is when you have zero lot line tolerances required by municipal
Ah,
bylaws or building codes where you actually cannot do vented soffits. And now all you have is a vent at the top. And what you
really?
fundamentally do is you now short circuit that ventilation. So that could cause
Absolutely.
low ventilation rates.
Right, right. We also get other things we'll see, like modern architecture with little flat roof sections that penetrate up through that are areas that can't be vented. So maybe we're
Right.
limiting how much of our soffit we can vent due to roof design. So there's lots of reasons for it, possibly
Yeah.
for it. But let's
Yeah.
look at what happens when we only get half of the ventilation we need. When there's no snow on the roof, it doesn't really affect anything. Looks exactly the same as before, in case you're wondering. Now we get 1 foot of snow on what we're calling a poorly vented roof. We're getting a huge jump here, 5 degrees roughly jump in the surface temperature of the roof. And we're getting a lot longer and more air times where we can get melting and ice formation under that
Okay.
snow. Okay. When we move to 2 feet of snow, now it still jumps up pretty significantly, another probably 2 degrees,
Oh.
which pushes us up over freezing in some different areas and makes these a lot longer, right?
Mhm.
Even from 1 foot to 2 foot, there's a large difference here, especially when we're talking about a weather where we're just on the verge of thawing or freezing. You're not thawing.
Right.
And then finally, the 3 feet of snow, where it jumps up again about another degree. Not as big a jump as from 0 to 1 or 1 to 2, but still probably pretty significant. So let's see what that looks like in snow melt degree hours. So this is the data I showed you before, the fully vented roof, and how many at 0, 1, 2, 3 feet of snow. Now we look at our half vent. So now we look at 1 foot of snow. We're already at our 1,000 here.
Mhm.
So now we're already sort of on the verge of having a problem, I think. And as soon as we get to 2 and 3 feet of snow, we're double that. We basically double the number of snow melt degree days going from 1 feet of snow to 2 feet of snow. So the fact that we're not fully vented, the amount of snow now makes a bigger difference than it did before because we don't have that air taking the heat away from underneath it as much as we did before. And so this really, to me, demonstrates the importance of the quality of the ventilation in that attic.
Yeah.
Whereas we can tolerate, I think, 1 or 2 feet of snow, maybe even 3 feet of snow with a well-ventilated attic. As soon as we get 1 or above with a poorly vented attic, we're going to end up jumping off the charts here with our how much ice formation we're going to have.
Right.
All right.
Okay.
So that's just the effect of the amount of snow on the roof. Then I wanted to look at what are some of the other effects of the other factors we're looking at. So the first one I wanted to look at was the effect of air leakage rate.
Mm.
And so I ran a series of models. This time I kept 2 feet of snow for all the models, R50 in the attic. And then the attic ventilation, the same as before, full vent and half vent. Okay. And what we can see is that at the equivalent 1.5 ACH 50, we went significantly. This is what we were looking at before at 3 ACH 50. We get a significant improvement below 500, even with 2 feet of snow, right? And even with 2 feet of snow, if we go to 5 ACH 50, okay, we jump up significantly in the number of snow melt hours. And that's in the fully vented case.
Right. And so so if the house is tight, 1.5, sort of a nice R2000 net zero benchmark,
Yep.
there's less heat and moisture arguably going into
True.
the attic.
Yep,
right?
that's right.
Which again, makes sure that the attic stays colder and controls the moisture, but it also keeps the plywood closer to the outdoor temperature and moisture content. I remember someone, it might have been you or John Straub, made the comment that fundamentally, vented or unvented, we're trying to accomplish the same thing. And that's to make sure that the roof ply stays at the same temperature and moisture content equilibrium as the outdoor environment. The minute we change that, we start to have issues.
That's right. And that comes down to, yeah, what the dew point of the air is inside that attic. The more interior air leakage air we get into there, right, the higher the dew point
Yeah.
gets, the more time we have for condensation and frost formation.
So Trevor, I'll show this later, but those calculations we did on the house of how much moisture. So a house that is at 2 air change, so even a little better than code,
Yep.
um, and a little bit of moisture going into the attic. When you calculate that across the day, it is 24 pounds of water, or 11 liters per day of water are going into that enclosure.
Yes.
And that's at 20% RH in the house. That's incredibly dry. So even if you live in Alberta or Whitehorse and, oh, it's dry in our homes, that's 20% RH. If you go to 40% RH, it doubles. It's 22 liters.
Yeah.
That's a lot of moisture and heat in that attic.
That's right. And if you have proper ventilation, it gets swept away by that ventilation. But when you don't, you start to have, so yeah, I always think about this as the balance. Have you ever seen Straub's moisture balance?
Right.
This is a perfect example of it because we have moisture being fed in to the attic from air leakage, and we have moisture being removed from ventilation. And it's all about that balance. And as soon as we tip it one way or the other, if we have too much air leakage or we have not enough ventilation, it tips towards having moisture problems, tips that balance, right?
Very good.
So the other thing we looked at was the effect of air leakage with when we don't have a good, well ventilated attic. And so we could see that even if we don't have a well ventilated attic, we have 2 feet of snow, but we have good air tightness, we can still stay below that 1,000 mark. But as soon as we start to have average or above average air leakage into that system, we can't get rid of it fast enough through ventilation. So that heat builds up. Moisture would be building up also. I could have, if we had time, and this would be a great topic for another day, would be what's the moisture content of that sheathing doing? But that from the inside moisture, that's a different topic, but
Yeah.
very related to this, especially to this aspect. Yeah. Okay. So again, once we don't have a properly vented attic, the effects of air leakage really start to play in. If we have full ventilation, we can get away with average air tightness. But if we don't have good ventilation, even average air tightness is going to cause problems once we get 2 feet of snow on the roof.
Great.
Yeah. Next, I want to look at the effect of the amount of insulation. And again, this was using 2 feet of snow again. This time I used only an air leakage of 3, ACH 50. And then again, our 2 attic ventilations, fully vented and half vented. If we had code levels of insulation, let's say R50, versus taking some away. So we only had R30. Now we could go from sort of well below 1,000 to over 1,000 of our melting degree days, snow melt degree days. If we add more insulation, we can improve it slightly. And these effects aren't huge in the fully vented attic, but again, on the poorly vented attic, they make an even bigger difference. So we can, make a significant improvement in how much snow melt we have, even if we don't have a perfectly well ventilated attic, by going from R50 to R70. And if we come up short on our insulation, whether it's because it's an old home or, someone's cutting corners, we're really pushing our risk now up to twice as high as what I think would be safe at 1,000. Yeah. So venting can help maintain, some of these not mistakes per se, but design imperfections.
Mm-hmm.
But eventually they can start to still become a problem even with full venting. And if we don't have full venting, proper venting, then these design imperfections start to really create problems.
Right.
Okay, so we talked about vented roofs. I wanted to kind of quickly and in a similar way talk about unvented roofs. So the first thing I'm going to show is an unvented roof. This is basically designed at 100% of the insulation on the exterior of the sheathing, right? Continuous air barrier, and no ventilation in the roof. So just layer of plywood, and then let's say shingles applied direct. So I'm calling this the direct applied shingle roof, unvented roof. Too many words.
Mm-hmm.
So now, because of the way this is designed, if we do it properly, we have a significantly less air leakage because we can have this continuous air barrier and we can use rigid insulation on top of that to create more air tightness and to protect our air barrier. So in the models, fair or not, I just kept air leakage out of them. Air can get into here. It's no problem, right? We're not going to have any problems until it makes it all the way through to under here. So in these models, I'm going to assume that there's no air leakage.
Okay.
And we're just going to look at the other factors that we talked about, how much snow is on the roof and how much insulation we've got. So the effective insulation. So we started with just using R30. So we'll just call it a code compliant unvented roof. Direct applied roofing, no ventilation, no air leakage. And so here's what we can see. A foot of snow, we're still well under 1,000 here. But once we get 2 feet of snow on this roof, we jump up significantly, right? So can kind of consider this or think about this like an interior-exterior insulation ratio. As we start to add more insulation to the outside via snow, we're going to warm up the temperature of the sheathing. We're going to have more melting.
Right.
And once we get to 3 feet, we're seeing numbers of way higher than we'd seen in any of the vented scenarios.
And this is interesting, Trevor, because this is some of the first time I think we saw this at Building Knowledge and Construction Instruction was actually at altitude, where they had a lot of non-vented roofs. Part of it was because they were making them airtight, a lot of passive designs, exterior insulation, and then putting the mechanicals in the attic. But we started to see issues, and that's interesting. And again, that reminder that the additional layer of snow creates a microclimate between the snow and the ply and the roof deck.
That's right. It's like it's adding insulation that can melt when it gets above freezing. So yeah, pretty extreme jump, especially when we start to get up to 3 feet of snow. And this is a perfectly airtight roof at this point in this model, right? So you could have great air tightness and still potentially have ice damming problems with an unvented roof. So what can we do about that? The biggest thing I think we can do is we call it over-roofing or steel overstrapping, basically creating an air gap between the roofing layer and the insulation layer. Okay. So even if this was a plywood layer here, and then strapping, and then another plywood layer and shingles, that would sort of represent this. What we're allowing is ventilation of this space and decoupling from a temperature standpoint of the roof sheathing and the shingles from the insulation.
Okay.
So a mini, what we call, probably rightly called a ventilated or a ventilated cladding roof system. Just like we have ventilated cladding walls, right?
Yeah.
It's not a true ventilated roof.
Right.
It's it's not a true vented roof with an attic, but it's a ventilated system that does allow that. So not even talking yet about what this could do to help you with moisture that could be potentially coming through here. That's another topic. But what it does to the temperature here and the amount of ice formation is pretty interesting.
Okay.
In this case too, I had to pick an air leakage rate or a ventilation rate, I should say, for this cavity. Again, doing some research, we can see walls properly ventilated cladding walls can have up to 300 air changes per hour. That's going to get less as we move less vertical and more horizontal. So
Sure.
but conservatively, I used 5 ACH again, just like for the attic
Okay.
above. So what does that look like? That looks like this over here. So here's our fully unvented roof, and here's our over-roofed, unvented roof.
So the vented, non-vented. The new
Exactly.
term.
Yeah. Ventilated, maybe, but
Yeah, there you go. There you go.
yeah, it's hard. So what we can see that once we do that over roof and have that airspace below that we can move air through, whether it's by strapping and putting steel on strapping or building up a second over roof, even up to now 2 feet of snow on that roof just gets us to 1,000 snow melt degree hours. Only once we get above up to 3 feet of snow do we start to see probably any significant melting, but such a big difference from the direct applied. And so now we can start to compare vented roofs to unvented roofs with this overroofing system. And they can both, I think, perform just as well.
Yeah.
Real quick, when to consider an unvented roof. If we have complex roof lines, for sure, where venting is just difficult to do.
Yeah,
If
Trevor, I want to just take a quick minute. Sorry. And let's put a pin in this. You'll notice Trevor has now transferred over to talking about unvented. So one of the things we just want to make clear is that we do see areas, and Trevor's going to talk about that, where non-vented roofs are a better option than vented roofs. And it's when and where do you make those transitions? And so Trevor's going to talk about that in a minute. So I just want to make clear what Trevor's been showing isn't that non-vented roofs don't work. It's just in some scenarios, when you have high snow load, you have to be, again, very careful about those areas. So
yeah, and if we're talking about ice formation and ice damming, and that's a big concern because of where we're building.
Yeah.
For example, Muskoka,
Yes.
which happens to be where a lot of my investigations occur because of that. And because we have complex roof lines, vaulted ceilings, low slope or even flat roofs, right? Once we get into these can't be properly vented in a lot of cases. Certainly, if we're going to try and put ductwork in the attic, we want to consider an unvented roof. We do not want to put ductwork in a vented attic.
No, it's horrible. And just so you know, folks, Trevor and our team both have seen when you try to do a vented attic and you think you're going to put ductwork up there and spray it with closed cell foam, it doesn't work. You're asking for problems. If you're going to stick mechanical systems that have depressurized airways, you have to do a non-vented attic. Don't fool yourselves with the spray foam.
That's right. And then lastly, and this is specific to my work in the Arctic, is concerns about snow intrusion into ventilation. So vented attics just don't work in the Arctic because of how fine the snow and how much it gets blown around and blown into attics. And so that really does push towards an unvented roof. So real quick, a couple of options for that. Exterior insulated, right? So that same sort of example that I modeled, which is all of the insulation to the exterior of our sheathing, a continuous air barrier below, right? This is the perfect roof in some building science terminology, that colloquialisms, right? In this case, our sheathing's always warm. We won't get condensation, right? But we still want to think about that airspace below there if we want to avoid ice damming. Another way we could do it is split insulated, a certain amount of rigid insulation on the exterior and a certain amount of air impermeable insulation in the structure. Really important that the air barrier is continuous, that we have the right ratio of interior to exterior insulation if we're going to do this. Again, looking at our data too from our modeling, we want to use higher than code required insulation and that ventilated overroof if we want to avoid ice damming risks. But can be done. This is exactly how my garage was built. It looks a little, the exterior insulation is a little thicker than this, but the same idea. And it seems to be working really well. This is the most popular or most common one I see in reality, which is the spray foam, closed cell spray foam roof. The important thing to remember about that is that spray foam is not just acting as our insulation, it's also acting as our air barrier. And continuity of that air barrier is critical. So any areas not covered with spray foam, doubled up rafters, beams, etc., have to be sealed independently of the spray foam. All of our insulation's interior to the structure here, so we have to make sure we don't let any moisture get through the insulation and to the sheathing, where it can deposit its moisture as condensation. And again, we also have thermal bridging in this scenario where wherever the wood members are, we're going to get higher, warmer temperatures at the sheathing. So we definitely want to use more greater than code required insulation if we want to avoid ice damming, and also the over-roofing to control ice damming.
We're at about 10 more minutes, if that's okay.
Okay,
Trevor.
that's good.
We'll
Perfect.
go to Q&A. So
that's perfect. And then lastly, of approaches is flash and bat, which is using closed cell spray foam and a bat insulation or blown in insulation in combination. Again, the air tightness of this closed cell spray foam is super important to avoid problems. We still have some thermal bridging here, but this might be a more affordable way to get higher insulation levels. We do have to worry about the ratio of the closed cell spray foam to the bat or blown in, make sure that that's appropriate for our climate zone so we don't get condensation in here. And again, to avoid ice damming in a roof like this, we want to use more than code requirements in terms of insulation levels. And we want to add that over roof or ventilated steel roofing to that. And then just to add a couple different things actually related to this, in terms of air leakage and air tightness, and for these unvented roofs to work properly, it really comes down to penetrations and transitions. Just a couple of examples of different transitions, wall to roof transitions that I've helped develop for different clients for different reasons. These are really important details that they get designed properly and then they get constructed properly to avoid air leakage into soffits, which is a really common problem, which could cause ice damming, can cause mold and moisture problems inside the soffit. So really important not to get into the nitty-gritty there. And then just generally, spray foam is an air barrier. It's really critical that we have thorough quality control and inspection when we're using spray foam in a roof, and it's our air control layer. We want to make sure that the spray foam's installed in adherence to the CAN ULC standard, that we have proper control of the substrate surface conditions, temperature and moisture content, that the installer has good access and can get the right gun angle to get to all the areas he needs to get to. Top of walls is a really common area for spray foam to not quite make the fill and have air leakage, as we see here. And then, as always, being aware of putting in too much spray foam too fast. So 2-inch lifts for closed cell spray foam is really the maximum. And multiple passes give us better curing and more chances to make proper air sealing when we use spray foam as an air barrier. Also, just as a quick example, because this came up recently with spray foam roof, trying to create a vented spray foam roof, we have to be careful. This example is where cardboard baffles were stapled to the inside of the rafters to create a vented space above. However, cardboard is not a proper and appropriate substrate to spray against, and the shrinkage forces of the spray foam overwhelmed the connection because there was very limited connection between the spray foam and the rafter, and we ended up with huge cracks and huge problems. So I always, when I talk about spray foam for roofs, it can be a very good solution, but it has to be done very carefully with really high quality control and always to the CSA standards. maybe real quick, if we have time for one. Why don't we do
Yeah,
questions? Why don't
yeah,
we do questions first? Because that might be cool. And if not, I got a couple case studies I could run through.
sure. Okay. So let's, I'm going to be judicious. We've got about 16 questions, lots of good questions
Okay,
here.
yeah,
Some are
let's do
maybe
that then.
more comments or others. So Ken just says, so I'll try. So when you have air leakage, how do you know how much is into the attic? And we tested ACH, that is the house, not only the attic. Um,
Right.
so maybe I'll take that one real quick.
Sure.
Ken, one of the things that can be done if it's an existing home is you can actually do a zonal depressurization. Our team does this often where we actually will depressurize the home and put a separate pressure monitor into the attic and in the home and outside. And what you can see is you can see the pressure difference. If you depressurize the home at the same time you do the attic, then you know there's a connection. And so that's one way that you can find out, wow, how much connection there is between the attic and the home. And of course, you do your calculations on surface area and flow rate and CFM and things like that, and you can pretty well identify that.
Yeah, that's a great question though, because you can have a very airtight house and still have air leakage, moisture issues in the roof.
That's right. We had a series of really well-built townhomes, three-story townhomes a couple years ago, built out of eaves. So very tight eaves, top to bottom, really tight enclosure on the wall, but the attics were not done well. And they had exceptionally high air leakage in there, and it was the shingles were prematurely decaying or starting to curl at about 5 to 6 years. So, Alan Taylor, as I listen to these presentations, my own experience, Trevor mentioned frost is normal. I wonder how much and what to look for. So this is a good one. So
Yeah.
Trevor, this I think a few other people would want to know too, because we know, for instance, in areas like Alberta and others, you'll get weather patterns coming out of the mountains where you will get, sort of moist air, maybe coming into the attic through ventilation, and then at night, you'll get that clear sky cooling. So now you've got cool surfaces. So you may get a little frost on some of the surfaces. I guess the question is, how much is too much? Maybe there's
Right.
not a clear answer on that.
The only clear answer is too much is when it melts and ends up getting down and touching drywall, basically
Right.
is the answer, I guess, because I would say any amount that is so much that it drips off of the surface of the underside of the roof deck is too
Oh,
much.
yes. Okay, so dripping, as opposed to evaporating,
Yeah,
or diffusing, right?
soaking into the plywood. Yeah.
Yeah. The other part too is, again, you can get a, $300, $400 infrared camera. You can borrow one from us if you want, but looking for cold spots, really clear blue spots on a ceiling is very indicative of pooling water, because water has a very, very high thermal conductivity, and you'll see ponding, and then you'll know that it's a bit much. Ian says, can the roof temp really get much above 0 degrees C? It will have ice cold water running. You're standing on it, and lots of heat will be used up by melting the snow latent heat.
Yeah, yeah, it definitely has to be just an hour above zero. An hour at 1 degree is not going to do much, but when you have multiple hours, multiple days, when certainly we have the sun that radiating onto a roof, that the roof temperature can get quite a bit higher than the air temperature due to that too. So it's
Yeah.
another factor in play. But yeah, that certainly eats up a lot of energy turning ice into water for sure.
That's right. And what's interesting is it eats up energy, but when ice freezes, remember, to your point, it releases a latent heat, and that heat continues to move up and melt the snow above it. It's the ice lensing phenomenon, right, that we see below ground. So, um, uh, Ali Reza says, what's the best thing to do when the downspouts are frozen, blocked by ice, and having an ice dam around the top? Trevor?
Yeah, that's a tough one. Certainly, I've seen heat tracing through. I don't recommend it, but sometimes it's the only option to run a heat trace down the downspout. I at my house at times will just remove the downspout for the winter, but
Right.
that's a little tricky too, because then when it does switch quickly, you end up with water where you don't want it. sometimes. So
Yeah.
that's a really tough problem. I think the idea being you want to limit the amount of melt and ice formation so you don't have to do anything about that.
So it's sort of a Band-Aid, but you're right. Little ice melt
Mhm.
lines from Canadian
Yeah.
Tire. Aaron, our good friend Aaron Grin is on here. So Trevor and Aaron worked together for years. Aaron's a great building science mind over at DuPont down now. Aaron says, how does the analysis look if you're dealing with an old R20 attic?
Yeah. Well, we had an R30 version, so getting pretty similar, right? Yeah, that much more heat loss means that much warmer temperature in the attic, which means that much warmer roof temperature. So
Okay.
yeah.
Okay. Justine has a question about spray foam as an air bearer. It's installed in ideal conditions according to the ULC standards. Is there still a chance of issues if the underside of the roof sheathing gets wet over time, or does it not get wet thanks to the spray foam?
So if it's done in an airtight manner and installed properly, the sheathing should not get wet due to vapor flow or airflow. So then, as long as you don't have a roof leak from above, there should be no source of moisture there to make it wet.
And as long as that is a closed cell spray
Oh,
foam,
so
not
thank
an
you. Yeah,
open cell, right? That's a big
definitely.
issue. Yeah.
Definitely.
Jason, snow blowing in through attic vents supposed to dissipate through a process called sublimation. Ah, yes. If there's warmer weather and sublimation is not completed, the snow melts, ends up leaking into the home. How can this be resolved? Attic vents, different vents, non-vented system altogether.
Yeah. So we've had in my work in the Arctic, we've had some success with baffled vents.
Mm-hmm.
Basically a tortured path for the air. Basically, what you have to do is slow the air down so much that it drops its snow. So it dramatically reduces how much ventilation gets through, but it also can reduce or eliminate the snow following the air in. So create a tortured pathway for that air on the way in.
Right, right. And when we have scenarios like that, and we do see that across Canada and in the northern US, where you get the really dry snow, the fine crystals with the wind will blow up into the soffits, it'll come in. So to your point, Trevor, get vents that actually restrict, and there are some that are better against blowing small crystallized snow getting in the attic. The next thing we would say is your next step is once it gets in, make sure that you are keeping the attic cold, right? And again, that goes back to Trevor's point. Make it airtight to the inside of the home and have proper amounts of insulation. Justine, what point does better than code insulation become redundant? An extreme example be 100 in attic space. Your typicals are 60. I'll jump in real quick, Justine, from an energy standpoint. I'll let Trevor take it from, I'm going to say, the building science standpoint. We find that we're sort of topping out at about 60 to 70, and that's across climate zones 4 or 5 all the way to 7 or 8. Now that is dependent on geometry, right, Justine? So if all of a sudden you're building an 8,000 square foot bungalow that's slab on grade, obviously the attic surface area is going to be a big deal, so maybe that makes sense. But for the most part, from an energy perspective, the ROI is around probably about a 60 or so. Trevor, from calculations though,
Yeah.
and your work, what would you say?
So similar for reducing ice damming is there's going to be a diminishing return as you go. I didn't go above 70 in my model, but the difference between 50 and 70 was still significant. So I imagine getting up to probably in the 80 to 100 range would still show a significant improvement in reduction in ice formation. So, but there will be a diminishing return for sure for every R you put on.
And then you also have the fact that if it is a hip roof or you have the sloped eaves, again, you can, maybe go to a raised heel truss. In our experience, though, what we find is in the field, many will say, well, it's a lack of insulation. We'll go in. There will be R40 at the eaves. And it's actually the issue with the ice dam is the air leakage coming up from the wall. And it's not the having the R40 versus the R80. So check to see, make sure you do both of them. And to Trevor's point, make sure it's airtight and then add that insulation and you're in really good form.
Yeah, yeah. Whenever I have attic moisture issues, my default is to first look for air leakage problems. And
Interesting.
then after that, move on to leakage from above or, yeah, ice damming.
That's interesting, Trevor. Yeah. So Tammy, what is the ratio for interior to exterior insulation?
For Southern Ontario, about 1/3 exterior, 2/3 interior can work well.
Yeah.
As we get colder, we just want to add more. There are tables available. I'm trying to think of a good reference. Maybe I could put something in my slides.
Yeah.
Put a good
And again,
reference slide in there. Yeah.
and again, it'd be a little bit different than the inboard outboard ratios. It might be as those apply to walls, but that might be a place to start. But when you are looking at horizontal surfaces, you will have an increased, I'm going to say, convection because of the surface facing up. So yeah, Trevor, if you could provide us with maybe something that's a little bit more, that would be
Yeah.
awesome.
Yeah, I'll throw a reference in the slide deck when I send it out.
Okay. Can you provide more details why we shouldn't have vented attic with mechanical in the area? Would an attic truss insulated air sealed from the rest of the attic remedy this? Do you have any literature on this? Justine, we have more than literature. If you want to contact Trevor or I, we have case studies. This is actually one of the reasons why our friends south of the border in the US, recent building codes are starting to limit their ability to put mechanicals in the attics, which they've loved to do for years. It is a real issue. What Trevor, I know what we find very interesting or confounding sometimes is the houses that have the worst issue with trying to put mechanicals in attics are actually big custom homes. We tend to be able to do this in affordable housing, but we get into these big custom homes. Nobody wants bulkheads. They don't want to see it. The problem is they force a situation that simply does not work well. So again, go ahead and reach out to us and we can try to help with that.
Yeah, I'd say in theory, it's possible to make the ducts tight enough to do that, but in practical terms, it just doesn't happen.
Yeah. Berlin, is it really important to run roof strapping vertically versus horizontally? So that's an interesting one, right? So for the over roof design, Trevor, does it make a difference?
Yeah. So in an over roof situation where you're putting an extra layer of plywood on, you definitely want to put the strapping on upslope and not across the slope to allow for that free air movement from top to bottom. Let the stack effect help you. When it comes to putting a steel roof on, double strapping is typically the way to go, so that we have proper support for the steel and pathway from eave to peak.
Mm-hmm. I do want to address something. I see it came up on one of the questions, and I just want to address this. We had a question about what about having attic fans? What about, having some sort of mechanical that would actually bring more vent in? Trevor, take a shot at that one.
Yeah, so the problem with an attic fan, assuming it's a fan that blows air out of your attic, is that it creates a negative pressure in the attic. So it will increase the ventilation, but it will also increase the air leakage at the same time from the house to from the house into the attic. So you may not be tipping the balance in the way you want it to. You may just be having more ventilation and more air leakage and end up in the same place that you were.
Yeah, that's right. I think many folks remember the squirrel cages, we used to call them. That was for a while. We used to think that was the answer to ventilation, is we'd put these wind driven, right? They would go up, the wind would blow, would turn it, and it would actually create a higher pressure differential to suck in the attic. We found that a lot of those attics actually were made worse because, to Trevor's point, what should have been done first is the insulation should have been removed. They should have made the ceiling plane airtight and then seen what happened before they had those units in. Gord tells the story of years ago on some affordable housing in the north. You would see the squirrel cages go in, and 2 months later, you would see plastic bags over the top tied off. The non-vented, sorry, just real quick, ice and water shield. Ian has a question about ice and water shield membrane. Is it effective enough as a solution if you've got a troublesome roof without trying to do some remediation around warming, around the warming surface?
Yeah, certainly it can help for sure. Depending on where it is and how it's installed. It gets a lot better than having just shingles that water can back up through. But there's always joints. And hopefully, if it's done properly, that even an ice dam won't create a leak if you have a proper roof underlayment system in place. But there's always the risk, right? Because there's still joints, even if they're lap joints or vertical joints in that system.
We had a scenario where we had a client that had done that on a low slope 312 pitch, and they had reshingled, put ice and water shield all the way up, interface with the wall. However, what we forgot was that they still got ice dams, but the ice dams built up down into the downspout, the trough, and the trough backed up under the roof sheathing and still leaked back up into the house, froze right back up into the soffits.
Wow.
But next question is anonymous. What if there's a non-vented cathedral with 7 inches of closed cell spray foam in the cavity and no exterior insulation?
If that closed cell spray foam is airtight and doesn't allow any moisture from inside the building and moisture-laden air from inside the building to reach a cold surface, then that can work. Although without the over-roofing on top, you're still going to get ice damming. But
Okay.
that ice damming may not end up coming inside the building depending on what kind of roofing membrane you've got or what kind of underlayment you've got.
Okay, we're sort of coming up here. We do have a little time. Ian, ice. Okay, so we answered Ian's question about the ice and water shield. Jeffrey St. Pierre had a comment. Thanks for chatting, Jeffrey. He had a case where they added wall insulation and it caused ice damming. Heat that caused to escape through the walls was contained and chimneyed up to the roof instead. Sort of an interesting house system. I did also see, I don't see it in here, there was also a little comment that was asked, I believe it was Deerish, that asked the question about dark surfaces. Trevor, this is something that you and I think have run into, is we do see darker colored sidings and darker windows and surfaces. And I think Darish brings up a good point, right? Because those darker surfaces, when they face south, you can get a large plume of warm air that starts to move up into that attic space. I don't know.
And just heats the underside of the sheathing in the soffit, right?
Yeah.
So you could definitely get localized warm spots due to that. What I would say about that is it's at least in Ontario, we don't have a lot of sunny days.
Right. That's
Even
right.
then, it would only happen during the day and not at night. So it could happen, but I wouldn't call it one of our major concerns because it's doesn't happen for many hours of the winter.
Enough, yeah. And maybe also happens sort of later in the year. Again, I think a lot of this too, let's just remember it still is good to keep the roof cleaned of snow. So if you do have cottages, if they are lower slope roofs, 312, 412 or less, let's try to keep those cleaned off a little bit. Jason, is there a settlement factor on R50 attic insulation and how can this be calculated? This is an interesting one. Trevor, you want to talk about that a little bit, or?
Well, I don't have any specific data on that, but what I do know is that as insulation gets denser, its R value per inch goes up. So even though there's less number of inches, the R value per inch is higher. It may not be performing quite as well as it did when it was full thickness, but I don't see that as being a major concern.
We see a lot of attics too, and oftentimes when the attic is, I'm going to say when it is properly installed, it's actually put into the attic or dispersed in such a way that settlement is expected. So oftentimes the blow-in is going to be several inches higher than where it may end up at. Aaron, are the gaps allowed by code sufficient for ventilation, or should we be doing more? So isn't that interesting? That's the eternal question. Where did the 1 in 300 come from? And of course, we know the history on that is more of a thumb in the air than it was an actual calculation. Trevor, what's your take on that?
When it comes to ice damming, the more the better. So I would encourage, if ice damming is a concern, then I would encourage going beyond the code requirement for that. There's probably some, some point at which there could be a negative to that. I guess having too many holes near the peak of your building could potentially just, be a risk of water intrusion or snow intrusion up there. But from a
One thing-
ventilation standpoint, I think more is better.
Yeah, the other thing too, just one point we often see in attics, new and existing, is even though there is proper size soffit vents and properly allocated ridge vents up at the top or at the peak, is that when you get inside, we find that most of the rafter spaces have been baffled off, and there may only be like a more vent or a small vent in, let's say, one in every four, one of every five.
Yeah.
Well, that's fine. You might be within code. However, if you're building a lower slope roof, and if you are in an area where you do have high snow loads, and if you are concerned about ice damming, we would say spend a little more and do every space with it. I think, what are they, 40, 55 cents a piece or something, right? So, all right. Alareza, I think we actually, sorry if I didn't pronounce your name right. I think we answered that one about the attic ventilator or the raised profile roof vent. Again, just be very careful. I think to Trevor's point is if you try to do something like that, just make sure that the ceiling plane is first made very airtight. Trevor, we do have about 4 minutes. Did you want to show that case study real quick?
Yeah, sure. There's some sort of relevant information in that. Let's do this. I've got two, but let me do the first one because okay. Oh, of course, I clicked too many times. Okay, so case study one was an unvented roof in cottage country. And you can see that it's got some steep sloped sections and some low slope sections. The issue, I guess I go to the next slide. The issue being ice damming, in some other clues being frost patterns and snow melt patterns that were pretty unique. And the main issue from the homeowner was ice formation in this corner, which I can show you. Just let me jump back really quick. Was this corner right here. So ice forming there all the way down to the roof below. And then eventually this has kind of been repaired, but some water marking, which happens to be above a shower or above a tub in the bathroom. I was talking about this earlier a little bit. The homeowner called a roofer to find out what was going on. The roofer said, it's because your roof is unvented and you need to add an over roof onto this, and that'll cost $50,000. And the homeowner said, hang on just a second, let's look into this a little further. And that's when I got involved. There we go. So a little bit of the investigation. Oh, sorry, did I jump ahead? Yeah. From the outside. So the soffit had already been opened up in that area. We did notice that there was a lot of mold growth and just sort of a general moisture and mold growth in that vent space. It wasn't just, didn't look like a point source of moisture to me. It looked like high humidity, which made me start to think more about air leakage. Okay, so that's what it looked like from the outside. And luckily this was already opened up. So I just had to run up a ladder and check that. From the inside, what I did is I pulled a negative pressure on the building and ran around with my IR camera.
Yes.
And there was a couple of really obvious things. And one was right here above the shower, which is where the water damage had occurred. I actually did a scan before I went under pressure, and there wasn't a mark there. There wasn't a cold spot there. But once the building was under negative pressure, there was. Opened up that area and found that there was a 3-ply beam running across. This is a spray foamed roof that runs up on both sides of this, but this beam penetrates through.
Interesting.
Can't see it in this photo, but if you look carefully, you can see daylight from a couple of the gaps.
Interesting.
What does that look like from the outside? Here's the end of that beam. From the outside back up in soffit, which I didn't see the first time because I didn't go stick my head or camera quite far enough up.
Yeah.
But once I did, I could see that this 3-ply beam, which was not sealed to itself, was penetrating through the spray foam.
Interesting.
Easy fix from the outside, air seal by using closed cell spray foam and sealing that from the outside. There was one other spot, and this is kind of a weird spot because this is where a vented roof meets an unvented roof. So there's actually a vented attic on the other side of this wall. And what we found was there was one, it's hard to kind of see here, but a plumbing vent pipe penetration that was unsealed and allowing air to flow from the attic on the other side of this wall. Or I guess, sorry, the inside of this wall into the attic on the other side of this wall. Again, really easy fix. Used some caulking and fixed the drywall and didn't cost the homeowner $50,000.
Wow. Interesting. No kidding. And again, to your point, back to sort of the air leakage conversation.
Yeah.
Yeah.
So I do have a slide at the very end, which actually I think, if I can get to it, I'll skip this one for now because we're at time.
Yep,
But
I think we're right at time. Yeah.
okay. So finding the cause of roof moisture issues, a couple things to look for if you're ever in the situation or trying to figure out.
Good.
Check the snow cover pattern on the roof. If there's no snow near the peak and lots of ice and snow near the eave, that's probably just a warm attic where the warm air is rising, things are coming down. So think air leakage there.
Right.
Look for if there's only like little areas that are clear and there's snow in the rest of the areas, then maybe you've got a point source air leak that can be fixed. And that's the case in the thing we just saw. Since I knew there was a kind of a point warm source or point source warm area, I figured it was a single air leak that we could fix. So go up in the attic. What's the condition of the attic? Check the RH, check for frost or condensation on the underside of the roof sheathing. Check the moisture content of the roof sheathing. It might not look damp, but it might be if you've got a pin moisture meter.
Right.
And then check for proper ventilation. All of this, if one or more of these is occurring, then it's very likely just general poor air tightness in the attic. The other one is check the condition inside the soffit, because a lot of times the air leaks we see are at the roof to wall interface. And if air is leaking into the soffit, look for things like, is it generally just moldy and wet? Is there one spot that's really wet and it gets drier as it goes away? That could differentiate between a leak from above and an air leak and just putting warm, moist air into that space.
Very good. That's
So
very
yeah, a
good.
couple things to look for if you're trying to narrow down the source
Yeah.
issue.
Yeah. I think we'll wrap it up, Trevor. I'll add one more thing to here. If you have access to a blower door, Chelsea Thomas asked a question, and I see we missed it in the Q&A. Chelsea asked about if you do have a blower door and you do a zonal test. So you're sucking the air out of the home, you have a pressure tap outside in the house and in the attic. And if when the house is at 50 pascal pressure difference, if you also see the attic being depressurized, you know there's a connection. And the question Chelsea asks is, what are we looking for? What difference? And we would say the answer is, in a vented attic, you should see no difference between the outside and the attic. Any sign that the attic is being depressurized is almost an immediate sign that there's an air leakage issue and possibly combined with a ventilation issue, but first and foremost, air leakage. So. All right, I'll share my screen, folks. I think we're going to have to call it a day. Trevor, that was phenomenal. Thank you very, very much.
Yeah.
That was good. And thank you, folks, for the really good questions. Like Trevor said, I think we could do another session here and we'd be all right. So hopefully you can see my screen there, Trevor. Can you see that screen all right?
I see you.
Oh, okay.
I did unshare my.
Hold on, I'll do this here. Hold on a minute. There we go.
There we go.
Okay, so yeah, we've got hang tight, folks, because you'll get the recording, you'll get all the notes sent to you right after you're done here. Please also keep track of our website notices. We're about to schedule our next series coming up soon. Sessions. Keep also on our Building Science Digest list. If you don't receive this, it's only done about 3 or 4 times a year. It's got all sorts of videos and details and highlights from the residential industry as it pertains to building science, cold climate building science. So again, I want to thank the Enbridge team for their support on these webinars. Stacy, thanks for the great managing the Q&A in the background. Folks, thank you for being incredible attendees with really good questions, and we probably could have a full day session on this. But first and foremost, Trevor, thank you very, very much for your help today. And if anybody wants to reach out to Trevor or Brandon or myself, all of our emails and access stuff will be provided when you get copies of the presentation today. So thank you.
Yeah, thank you.
Yeah,
Thanks,
great
everyone,
job,
for attending.
guys. Thanks for everyone attending.
Have a good Thursday afternoon, folks.
Take care, everyone.
Take care.